So I'm going to demonstrate stochastic gradient descent as well the original gradient descent um, for multi-class softmax based classification. Okay, so recall that in your homework number 3, you did softmax regression, and for multi-class classification, it was incredibly slow, even for a relatively small number of images that you sort of loop through or processed. Okay, so I want to show A, the power of stochastic gradient descent, and actually B, the power of automatic differentiation. Okay, in the previous gradient descent sort of implementation that we saw, the gradient was computed using um, uh, using finite difference approximations, which requires you to, if you have 785 variables, which is what your MNIST sort of regression has, actually for the uh, multi-class regression, you have 785 times how many ever classes you have, 785 being 784 plus 1, the number of pixels plus 1, times the number of classes. So it's more like 785 times the number of classes, which is, we have an optimization problem with 7,850 unknowns, um, which means that you'll have to compute the gradient, you will have to evaluate the function. Well, if you're using forward difference, at least that many times. And if you're using central difference, you need to evaluate the function close to um, 16,000 times to actually compute one gradient value, right? So we're computing the function 16,000 times to compute the gradient, because you have to perturb, take a step in each and every direction, once forward, once back, to compute the gradient. That's a lot of function evaluations to compute one gradient value, okay? Um, so automatic differentiation, like we said, doesn't do all these multiple function evaluations. It essentially does this chain rule to compute the gradient in a much more efficient manner, um, programmatically. Okay, so let's actually just look at that. So this is just gradient descent, but now implemented on the multi-class regression problem, the softmax regression problem. These are all just the setup stuff. So let me just walk us through that. Oops, I guess I haven't completed that sentence. I will complete that when we get to it. I'm using now only 6,000 images, just because we don't want to take forever to compute one gradient. Um, okay, so here we are evaluating the function once. The function evaluation took about 0.4 seconds. You can try that again. Now it took about 0.05 seconds. This thing, which one did it take? 0.05. So 1/20th. But then imagine having to repeat that 15,000 times. So actually, let me do, it's my gradient. So we're not even going to try to use the central difference formula to compute the gradient here. Instead, what we are going to do is use automatic differentiation. We are writing this new function, logistic loss multi-class with derivative. If I open that and compare it with the usual logistic loss multi-class. So this is the logistic loss multi-class objective function. It's just 3-4 lines, right? Z equals X times V, apply softmax, find cross entropy. This is identical. Z equals X times V, apply softmax, find cross entropy, except it has this additional sentence which says, if this is H, the output, we say dh by db, excuse me, equals dl gradient h comma b. In other words, we are finding the gradient of this function, the logistic class function, with respect to the input b, and providing that as an output, and evaluating the function using this thing called DLF eval. We've already declared our b input, our unknown variables, coefficients, using this DL array data structure, and that will tell MATLAB that any function that is dependent on b input um, will need to be dealt with differently, specifically with a view to propagate the derivatives of, or the gradient of the function with respect to um, these coefficients. Okay, um, so we are trying to differentiate the logistic class function with respect to these unknowns, b input unknowns, and then that's why we are evaluating this alternate function. Instead of just a plain function, we are evaluating this function which also returns the derivative. Um, so let's actually see how fast this function that computes the derivative as well takes. Let me run that. Oops. It took 0.5 seconds. Let me run that again. 0. 0.1 seconds. Oops. Let me run that again. 0.06 seconds, okay? 0.05 seconds. So computing the function and the derivative takes only about as much time as computing the function as at all. Okay, so it's remarkably highly optimized derivative evaluations, so much more efficient than running this function 15,000 times. Okay, so if you ran this function 15,000 times, you might be here for a long time. Um, so I don't know, 0.04, or let's say charitably 0.03 times 15,000, 450 seconds. So it will take 450 seconds potentially for one iteration, for one gradient step. That's a long time. It may be that the function evaluation will get faster as you repeatedly evaluate it, but it'll still be many tens of seconds to evaluate the derivative, very likely. But DLF eval cuts through all that and evaluates the derivative almost as fast as evaluating the function as well. I do want to notice, like I mentioned again, we are using tick and talk to evaluate how long something takes. These numbers, as you see, are variable each time you run the function. And that's because my computer is doing lots of other things, and uh, there is a lot of randomness in how long a function will take exactly to complete, depending on what other processes are running on a computer, etc. That's one thing. And then a single evaluation of a function might not be the most effective way to um, um, compute how long a function takes to run. So if you run it 10 times, let's say, let me just run that. Okay, it took about 0.1 seconds for 10 iterations, and then it took about 1 second for 100 iterations. Okay, what if we do the same for the gradient? So 15,000 would involve about 150 seconds if we go by this estimate. Okay, not quite 450 seconds, but 150 seconds or so, because subsequent function evaluations were a bit faster. Now let's see Um, so computing the function and the gradient took a little bit longer, but we computed the function and the gradient 100 times in 2.4 seconds. So 2.4 by 100. The function and the gradient in this case just takes 0.02 seconds roughly on average. Whereas if we used central difference, we would be here for 150 seconds. So automatic differentiation is 150 divided by 0.025 times faster, 6,000 times faster than using central difference formula and more accurate. Okay, so you should always try to use um, um, automatic differentiation if possible. So this was just for timing purposes that I did this. So um, we don't necessarily want to keep evaluating this lots of times. Okay, so now we have a way of using automatic differentiation to compute the derivative really accurately, really fast, almost as fast as computing the function itself, as opposed to 15,000 times as fast, slower. Um, so now we just do the gradient descent, number of steps, alpha, the learning rate. This doesn't matter anymore because we're using automatic differentiation. Gradient threshold is the same. We have the initial set of iteration, initial set of values for the unknowns. Um, Here we are just evaluating the function at the initial um, guess, initial seed, and then we are plotting the function value at the initial step. So it turns out that you need to use this function called extract data. So these f value initial and grad f are uh, are data in this DL array format, right? So they are data in the DL array format. So if you say H is 2.3026, but it's in this DL array format. So if you just go plot a or 1 comma H or something, it'll just complain. But then if you go plot extract data of H, then it will plot it, I guess. I need to, okay, so there's that point. So essentially to extract the number from that data structure, you need to use this thing called extract data. So that's what being used here while plotting. Let me run that. And then we can implement gradient descent. We are implementing gradient descent with 6,000 images, right? This is just regular gradient descent as opposed to stochastic gradient descent. We can use 60,000 if we want, but let's just use 6,000. Actually, let's use 60,000, I guess. See what that gives us. So it looks like the function of the gradient takes about 0.2 seconds to evaluate because it's now 60,000 images. This is actually pretty good. We are not necessarily plotting the, I'm plotting only once in 10 steps here. Rather than plot every step. So this is the gradient descent. Just to not slow things down by plotting every step here, plotting every 10 steps or so here. Okay, so this is remarkable. This is just plain gradient descent. Um, just using automatic differentiation allows you to do like uh, pretty fast gradient descent using the full data set, right? Using 60,000 images gradient data set. So it's pretty fast, just using automatic differentiation, okay? And then we can, I'm just going to Control C out here. And then we can use stochastic gradient descent. Um, like we did before, instead of using 60,000 images, we can use on each step um, a random sample with, let's say, 1,000 images or for 256 images or whatever, something. Um, let me just say 1,000, run it. So the idea is that this function evaluation could be faster because we're using fewer images in the um, when we are using when we're computing the gradient or the function evaluations. In any case, you notice that the optimization proceeds pretty fast, faster than before, certainly, and it's achieved what looks like a steady state. Maybe it will reduce a lot, but this will already be pretty good performance for your multi-class regression, right? So recall that in your homework and in your homework especially, multi-class regression took so long to make even small improvements. This algorithm, A, by using automatic differentiation to increase the speed at which gradients are computed, and B, using mini batch stochastic gradient descent to reduce the number of images per function evaluation, but then randomly looping through all the images allows you to go much, much faster. Okay. Okay. So um, the version of stochastic gradient descent that I just explained, where we're just randomly selecting, let's say, 1,000 images or 100 images from the full data set to process every step. That is not the most common way of implementing stochastic gradient descent. Common way is actually a slightly more deterministic, a slightly less stochastic version of the stochastic gradient descent, where here, so exactly the same as before. I'm going to call this stochastic gradient descent with epochs, or um, it's basically what people would call stochastic gradient descent in the literature these days in machine learning. Okay. Um, exactly the same as before. Everything's the same. We're going to use automatic differentiation, blah, blah, blah. Except the way we pick um, the mini batch. Let's say we have a mini batch size of 1,000 images. Okay. Um, Rather than just picking randomly 1,000 images each gradient step, what you do is divide the 60,000 images into sort of randomly selected sets of 1,000, and so on. So you divide the 60,000 images into 60,000 image sets, okay? And then you first use the first 1,000, and then use the next 1,000, and then use the next 1,000, and so on, okay? And this way, rather, if you randomly select 1,000 from the 60,000, you might perhaps um, uh, not necessarily loop through all the images in a short period of time. You may have not considered certain images for a while because you're just randomly sampling. This way, if you just divide the whole thing into sets with 1,000 and then just loop through all those sets, you will have looped through all your data once in 60 sort of iterations, I guess. And that looping through all the data once is called an epoch. Okay? It's called an epoch in machine learning lingo. Um, so what we're going to do is, but of course we don't necessarily want to literally take first 1,000 images as the first set, second 1,000 images as the second set. Rather, we because maybe the data is ordered in a particular manner and we want to have some randomness. So what we do is we randomly permute the training data. Okay, we randomly permute the training data so that 1 to 6,000 gets mapped to some other order, some other random order. Okay. Once you randomly permute that, you just go mini batch list equals. Um, you then take the first 1,000 from this randomly selected list, the second 1,000 from this randomly selected list, the third 1,000 from this randomly selected order, and so on. Mini batch is the same thing, and so on and so forth. Okay. So let me run this thing. So that's the idea. You take the full data set, randomly reorder it, and then take the first 1,000, the next 1,000, the next 1,000, and so on for each set. Go through the whole data set once, but now in some random order, and then repeat that. So here, instead of saying let's do 1,000 gradient descent steps, I'm saying let's do 100 epochs. In other words, 100 passes through the full data set, and each epoch consists of num train data, which is 60,000, divided by mini batch size, which is 1,000, so 60 mini batches. Okay. Of course, if you use 100 as a mini batch size, you'll have a 6,000 mini batches per epoch. Anyway, so that's also called stochastic gradient descent, except for these epochs business. And people won't say with epochs, usually this will be the most common variety of stochastic gradient descent in machine learning. So let me just run this thing. So I'm plotting only every 10 steps, and you notice that again it's running pretty fast. And I've drawn these vertical lines to indicate where each epoch ends. So from here to here, in these many iterations, that's actually 60 iterations, we have passed through the whole data set once, and then we pass through the whole data set once more, and so on. So by about 6,000 iterations, the full data set has been looked at by gradient descent 10 times, and so on. Okay. Yeah, so this produces a bit more sort of regular progress because it makes sure that all the data is seen at least once in a while, as opposed to some data never being seen or very rare, much more rarely being seen by random chance, which is what might happen if you randomly select data at each set. Okay, so sort of less stochastic gradient descent essentially. And it's still making progress, or maybe it's gotten to some kind of a steady state. But overall, it makes a rapid progress initially, which is very different, and using essentially all the data, right? Yeah. So that's stochastic gradient descent. So the next topic will be essentially putting together all these ideas, but now using them on a more sophisticated way of representing functions. So we use logistic regression here. We did linear regression, polynomial regression, and so on. If you wanted to approximate truly nonlinear functions, people have been using, there's lots of ways of doing it, but people have been using neural networks. Things very crudely inspired by how neurons work in the human brain or animal brains, animal nervous systems. So I guess that's going to be our next topic.